Okay, I want to leave this video for you guys to watch on Wednesday. A couple of things that we need to go over. I did the chapter assessment for everybody except Matt and Dave. I didn't get anything from you. I need to get something to me as soon as you can so that we can do that. But there's something that I'm a little concerned about. We kind of I thought we went over it enough, but apparently we didn't cover it sufficient. So there's a couple of things that I want to go over. First of all, remember that waves carry energy, don't carry matter. The way we tried to demonstrate and the way we've used this on a regular basis is that a boat sitting on the water, if a wave comes in its direction, the boat will go up and down, but it doesn't move with the wave. Okay, eventually, as the energy, some of the energy, of course, is transferred to the boat when it's sitting there as the wave comes over it. But generally speaking, the boat simply follows the wave up and down. So long, if you leave a boat in a wave form long enough, or where there are waves going in, eventually those waves will push the boat and carry the matter in, but the waves aren't carrying the matter. They're transferring their energy from the waves and from the water into the boat. Okay, so it's important to understand that there's a difference between matter and energy in this case here where it comes to waves, and this is going to be really important when we start talking about how energy can be transferred through something where there's no medium. So there's nothing in interstellar space that transfers the infrared heat, which is a wave form, to the Earth 93 million miles to land here on our planet and warm up our space, warm up the place where you're at. We're hoping that more of that's going to happen as we get rid of the snow. So that's one thing you got to make sure is, and I think all of you, missed that one, and you marked that matter and energy was transferred. It's just energy. That's the only thing that's moving in a wave. The example that we also used was when you have a seismic event. Remember, where you have two plates that are coming together, one driving over the top of the other. As they lock up like this, eventually this one here springs up, and when it does, it displaces all of the water above it to the same degree that it comes up here. Okay, and so as the water is displaced, then the water just goes up because it's displaced, because the matter here is moving up. It moves it up. It creates waves that fan out in 360 degrees, right, as it goes up. But that water that's right above the place that pops up here, it doesn't go anywhere. It just goes up and then back down. And so that's why we want to make sure that you understand the difference between the transfer of energy and matter, because what happens is the energy that pushed that water up is transferred in a wave, and that's the tsunami that hits the coast. Okay. Then the other thing that I wanted to kind of go again and talk about the difference between refraction and reflection. Kind of a difficult situation. One of the things you got to remember about refraction is that refraction is something. Well, let's deal with reflection first, because that's the simple one. Reflection happens when you're dealing with a situation where you have an almost exact return of where it's at. So remember, we're talking about the incident angle. So if it goes in at a specific angle to a mirror, it's going to come back out at the same angle. So if it goes in at a 45, it'll come out as a 45. If it goes in at 180, it comes out at 180. So that's one of the reasons, one of the questions was asked is, how come you can't see everything behind you in a mirror? Well, the reason why is not only is it not in your area, but only the light that reflects on the mirror directly into your eyes is available for your eyes to see. So the things that are behind you, you can do the same thing. A simple example is take your phone, turn on the camera, and face it towards you. The only thing that you can see behind you is what is within the area of the camera that comes from behind you. So if you're looking at this video now, you can see up over here I have a picture. right? Now I've got another picture over here. That's Sarah out on the grasslands up there. But those are within the area of the camera, the light that's going into the camera's eye. Okay, the things that are outside of that, my desk over here and the doorway over there that goes outside and so on, you can't see those because they're not within the frame of reference. So reflection is a reflection. Remember, one of the things that we talked about is we talked about the fact that things were one of the things that was required was that we have this concept of a normal line, right? Okay, and let me get a pen here, and I'll hold this up. So if we have a reflected image. Okay, so I'll put this up here. I don't know if you can see that. See how we have the reflected image, and the reflected image comes in this direction. It's going to reflect at exactly the same degree as it arrives, based on what's called the normal line, or the normal. Okay, so you see up here how this goes. This is normal, right? Okay, so the direct angle of incidence that comes in here, it will reflect at exactly the same angle out. Okay, so this is reflection. All right, so reflection is a little bit different than diffraction. Diffraction boils down to the change of the speed of light. Okay, so let me give an example. Let's see if I can find a better. Thought I had a marker here, but I guess oh, there it is. Yeah. Okay. So remember, one of the things that we talked about is if you have a pencil that is going into a cup of water, it will tend to look like this. Okay. It'll tend to look broken, and the reason why is because what's happening is that the speed of light out here and the speed of light in water are different. And so if you can see this, and one of the things that's interesting, you can try this, just take a glass of water at your house and put a pencil behind it, and you'll notice that not only is it in, but if it's behind the glass, because the light traveling outside the glass out here on either side, okay, so I can put a pencil that goes all the way through here like this. All right, and what you'll see is you can see there'll be a slight diffraction, and the reason why that is because the speed of light out here in the air is 300,000 kilometers per second. Right, it's 186,000 miles per second. Okay, so the speed of light in the metric system, in the SI system, is 300,000 meters per second. Okay, and so that's how fast that thing is going. 300,000. Okay, and so trying to remember all my numbers here. Okay, so then when it goes through this area, it slows down to some degree. It's not, we can't really see that much of it. It's hard to measure. We don't have the appropriate things to measure for scientific instruments, but our eyes tell us that the things have changed. And so that causes diffraction because there's a change of the speed of light, which is represented by the letter C. Okay, so for constant, that's from E is equal to mc squared. So the speed of light out here is 300,000 K. All right, so 300,000 meters per second out here. But in here, it's something less. All right, I don't know how much it is. We could probably look it up. But the idea then is that the reason why this is kind of critical is because if you look through this, you can see in this situation here, in this thing here, once it passes on this side, that the speed of light on this side of the glass and the speed of light on this side of the glass are exactly the same. Okay, they're equal. All right, so this is the difference between reflection and refraction. Refraction has to do with the change of the speed of light. Okay, and so as we see it, and so the speed of light that we're seeing, that's the waveform we're talking about. Okay, and of course we'll see this in other things. You can do the same. You can do the same situation as we saw in the book. One of the examples that we saw here is that when you have waveforms, it's on the top of page 342, and you can see that the waves hit those islands, and as it goes around those islands, those waveforms that go around there, they diffract, okay, because they change speed. It's not just because there's something in the middle. What causes them to change speed is that they hit the islands that are there, okay. And of course, one of the things that we also talked about is we talked about the interference patterns and so on. And so, in a quick review, if you look at the interference patterns that we're talking about, let me see if I can get the right one here. Look at the interference patterns. One of the things that's required is for the interference pattern for the slits to be very, very close together. And so if you have a light source on this side and it's radiating out over here, so you can see how the light source is radiating toward these two slits, right? And so what then happens is that those slits begin to radiate, each one of them in their own way. And of course, everywhere where you see where those cross in that situation, if you boil right down into those, what you would see is that you would see two waveforms. You'd see two waveforms that that look like this over and over again. And so everywhere where they cross, let me see, right here, everywhere where they cross, and I put a circle, you'd end up with a wave pattern that comes through that thing that's very strong. Okay, so then they begin to influence one another, and they either constructively or destructively coincide, or they interfere with one another. So if you have two waveforms that are going up at the same time, then they add their amplitude, right? If you have two of them that are going down at the same time, then they have the same decrease in amplitude, right? If you have one that's going up and one that's going down, then they cancel one another out, and you end up with nothing, all right? So that's how you end up with that pattern that we talked about, where you have light and dark spots. I've tried to replicate the two slit program. Is a little difficult to do, so I won't be able to do that. I was hoping to do that for an experiment for us, but it's a little tough. Some of the things, the equipment that I have to work with doesn't give me the ability to do that. So I'm looking into hopefully doing that for next year's students. So maybe you can talk to them about that, okay? All right, so the reason why I'm kind of going back over some of this and making sure that we see this in this deal is because we need to do a test on Friday. That's going to be what I'm going to ask you to do. So I'll get it set up. I'll get it sent out to you for Friday. For tomorrow, I want you to read this, view this video. Then what I want you to do is I want you to go back to the assessment, okay, and I want you to redo the assessment. The assessment was not very good from anybody. You missed a lot of the really critical things, and if you don't get this assessment, then your scores on the tests are going to be really bad. So I don't want that to happen. So if you can make that happen, this is about a 15 minute video, and then send me your chapter assessments as a redo after you've gone through this, because I want to make sure you grasp this stuff before we tackle the test. All right. Have a good day. Remember, we're going to get through this. We're going to make it. We can do this. I've been homeschooling for 30 years, so we know how to do this. We can make this work. It's not that hard, but it does require you to show some diligence. So you guys are old enough to step up to the plate. So I'm encouraging you to do that, and I'll be looking forward to seeing you all again, hopefully sooner than later. We'll see how things go. Have a good day.